Okay, good evening everyone. Thank you very much for turning up this evening. So I'm going to be talking to you about how we have been moving our application server density over from SoftLayer to Google Compute Engine and the Google Cloud. So my name is David Mitten and I'm the founder of Server Density. We do server and website monitoring, so we look at the performance and uptime of your website from multiple locations around the world and then get into the server internals to alert you, help you build dashboards and figure out what's going on your infrastructure. We have about 100 servers powering the service and they're all powered by Linux on Ubuntu 12.04. And it's about a 50-50 split between virtualized and dedicated. We process about 30 terabytes a month of incoming data, and in our largest MongoDB cluster, we write about 1 billion documents a day. Well, the product is powered by Python and MongoDB exclusively, and we use Nginx as a front end. And we're currently towards the end of our migration process, moving from SoftLayer over to Google Cloud. So there's a couple of reasons we decided that this was the right decision. And the first of these is the innovative pricing that Google has on Compute Engine. And back in March, they announced sustained discounts. And these can be likened to reserved instances on AWS, except there's no upfront cost, and you automatically get the discount at the end of each month based on your usage. All you have to do is use the Compute Engine instance for the whole of the month, and you get a 30% discount at the end. And this is really important for us as a startup. We don't have VC funding. We're funded on revenue and small angel investment, which means we can get the advantages of large capital outlay you have to do for reserved instances without actually having to pay for it up front. So it's a massive advantage on cash flow. I also expect Google to compete with AWS and Microsoft over the next few months and years, and we're going to see a lot of good competition decreasing pricing. But Google's come up with this alternative to reserved instances, which makes sense for startups. We're also able to take advantage of very fast global networking. This is because Google owns a lot of their own fiber connectivity, and all of the data centers in the regions are connected by very, very fast connectivity. Compared to AWS, for example, where although you've got connectivity within the zones, inter-region connectivity is still entirely independent. And this makes it quite difficult to set up geographic redundancy without going into running virtual private networks and those kind of things. So we can take advantage from this on Google. And to be fair to SoftLayer, they also have very good private networking. Within SoftLayer, you can deploy an instance or a dedicated server within any of their global data centers, and you get that appearing on the same private network, regardless of where it is. This is the same with Google Compute Engine. We're also planning to take advantage of BigQuery. We process a huge amount of data coming into MongoDB, and that's great for generating our real-time graphing, processing, alerting. But there's a lot of overhead involved with scaling Mongo to store huge quantities of data. And so we deal with this by removing data after a certain period of time. Ultimately, we want to build features around analytics of all the data that we've ever received. And we can do this in BigQuery because although Mongo is very, very fast at queries compared to BigQuery, which is a little bit slower, we can actually put more data into BigQuery. And Compute Engine itself is perhaps a surprisingly well-designed product. Google have taken what AWS and the other providers have built and learned over the last 6 or 7 years and created a new product which is very, very well implemented. All the features work really well, it's been properly thought through, and our testing and production usage has shown it's very, very strong. And also, perhaps surprisingly, Google do care about their customers. It's not just because we've been talking about it. I've been able to work directly with engineering teams on testing new features before they've been released. And they have been very responsive to feedback, both here in the UK and also over in the US. And just like AWS, you can pay for technical support. You can phone someone, you get an account manager, and you can submit technical support tickets, and you're going directly into the organization that can deal with it. And just on the networking point, I did some benchmarks a month or two ago. You can find the detailed methodology online at that URL, but you can start to see the difference comparing AWS and Google in this case, but I also looked at Rackspace and SoftLayer. And although AWS does give you higher throughput on their really high spec instances, the cost of those is significant. And if you compare the cost per CPU, the value is significantly better on Compute Engine. But also note the inter-region connectivity throughput. It's an order of magnitude better on Compute Engine, even on their cheapest instance, to transfer data between the US and Europe. And as part of our migration, there's a couple of steps involved with this. We've got 100 servers. It's not a trivial process. And there's a couple of main steps involved with this. And the first of these is simplicity. Now, I've talked about BigQuery, and there's a load of other interesting features that Compute Engine has, like load balancing, but we don't really want to use these all in one go. The first step is to migrate everything in a one-to-one fashion. We have servers at SoftLayer, and we can get servers on Google, and we just want to translate those over. And all the cool features like BigQuery and perhaps getting rid of Nginx and using the load balancing product from Google can come later. We really want to keep it as simple as possible so we can migrate with minimal hassle. And so there's these 4 steps that we go through: planning, testing, replication, and then finally switch over. And the planning step is probably the most important. You need to understand exactly what is going to happen and when. So there's a couple of questions. So for example, what is different on your new environment compared to the old one? So for example, we run Ubuntu on SoftLayer currently, but it's not available on Compute Engine yet, hopefully. Instead, we have to use Debian, which is almost the same, but it's not quite the same. Ubuntu is, of course, based off Debian, but there are differences and quirks that we have to work around. Are you using any of the proprietary APIs from your existing provider? For example, we tie into SoftLayer's IP address APIs so that we can do auto failover and move IP addresses around. This is proprietary to SoftLayer, so we have to re-implement this or understand how Google does it. And are there new things to learn? So when you deploy into SoftLayer, you go into a specific data center, you know exactly where it is. We're in Washington and San Jose. If we compare that to Compute Engine, it's US Central and EU West or Asia East. And these actually behave in a slightly different manner. You'll probably be familiar with regions from AWS and zones. You also know that zones are almost independent, but you can have whole region failures. Google's slightly different in that they say a region can't fail, and you have failure just of a single zone. And so the zones are considered data centers for all intents and purposes. So these slight concept differences are important to understand, because it means you can deploy in a single region and have full redundancy by deploying across different zones. And what are the costs to this migration? You can't just switch everything off and then switch things back on again in your new environment. You're going to have to run 2 environments for a period of time. And the point of the planning stage, unless you have unlimited amounts of money, is to reduce this time so you're not paying twice for both environments. You want to keep that time where both are running at the same time to a minimum. The next stage is testing, and we've spent a month and a half running through benchmarks, testing workloads, and making sure that our existing workload, which we don't have any problems with in SoftLayer, is going to run perfectly on Compute Engine. So how does configuration work? What do you need to do to work with the Google products to configure them in the same way so they'll behave in the same way as your existing infrastructure? And do you need to make any operating system tweaks that might not be necessary in your current environment? And how does networking work in the new setup? Do you have multiple interfaces? Are they different interfaces for public and private networking? And how does that all work? So when it comes to optimizing Compute Engine specifically, we can look at the product and start picking specific instance types for the workload. Now at SoftLayer, we're used to having very specific specifications. We run Mongo only on dedicated servers, and we can configure them exactly to the spec that we need. if you're using AWS, you'll be used to trying to fit your workload into the set instance types. And AWS does have a wide range of them, but you can't choose 6 CPUs and 1 gig of RAM. You have to fit within their instance types. And it's the same with Google Compute Engine. And specifically, we're using the high memory instances. Also, an interesting feature of Compute Engine is the fact that the disk volumes scale based on the volume size. And this is a great way to do it because it's incredibly simple. You don't have to figure out how many IOPS you're doing to understand what you're going to be billed, which is important. One of the problems with EBS, for example, is you can predict the size, you can perhaps predict the number of IOPS that you need, but the number of write operations that you're doing, in actual fact, after the case can be very difficult to understand what you're going to be billed. In contrast, Compute Engine, you just choose the size and you know exactly what you're going to be billed and how many IOPS you get for that. And this has changed in the last few weeks with the general purpose SSDs that AWS have released, where they don't charge for IOPS. You also have to be aware that VMs have limits too. So although the theoretical size of a Compute Engine disk is 15 terabytes, you could think that you will be scaling the number of IOPS all the way up to that. But in actual fact, you're going to be limited by the number of IOPS that a particular VM can do. And this differs depending on the VM type. And so you need to be aware that you're not hitting those VM limits when you think you're going to get a huge amount of IOPS based on the volume size. As Tom mentioned, one of the pitfalls is choosing a volume that's too small. And it's a trade-off between wasted space and using a single volume versus having multiple volumes all at different sizes. And so you need to understand the size of the volume that you need, not just for the amount of data you have, but also for the throughput. And RAID is already handled behind the scenes. You don't need to do this for your persistent disks or for your SSDs. They are already RAIDed, and putting them into a RAID array can actually reduce performance. Now, specifically concerning MongoDB on Compute Engine, you get those IOPS by resizing the disks. You can start off quite small, and then it's very easy to increase them. Although you can't specifically edit a volume size, you can use snapshots to restore them to a larger volume very, very quickly. And equally, you can restore snapshots to a different type of volume, so you can switch from spinning magnetic disks over to SSDs very, very quickly. The way we do this currently is by scheduling maintenance and having a data center tech walk into the facility and swap out disks, which takes hours or days because we have to do it in advance, whereas on Compute Engine, we can do this in a couple of minutes. And this is important to understand that the VM limits are there, and they are higher depending on the instance type, but it can be very easy to hit those limits and not understand why your throughput is being limited when you've sized the volume correctly. And SSDs are going to be very, very important. We are running some production Mongo instances on the magnetic disks, but they're not very high throughput. And to get the real performance, you need to use SSDs. They are more expensive. Standard disks are 4 cents per gig per month, and the SSDs are 32.5 cents per gig per month. Also, what was announced at I/O is availability of local disks, local SSDs. So the magnetic and SSDs by default are actually over the network. There's a nice SCSI interface. But although the Google network is incredibly good and is properly designed for this kind of performance, and they say you're not going to get the same kind of issues that EBS has been known to have with perhaps excellent throughput but latency spikes, you can still optimize this further, and you can get very high numbers of IOPS, into the hundreds of thousands of IOPS on a single volume, by using local SSDs. These are now in testing, and you can actually RAID them on the software side of things to combine multiple volumes to get larger disk sizes. Also, in my own testing and talking with the Google storage team, that you should use the Linux kernel 3.3 and above. There shouldn't be a problem on the default instances. It's been a couple of years now since 3.3 was released. But if you use a Linux kernel below that, then you can have performance problems. And interestingly, you can actually disable CPUs on Compute Engine, and you can do this and they'll become disabled to your instance, but behind the scenes they're still there and they can still be used by the storage infrastructure. And this means you can give storage dedicated CPUs. Now Mongo is almost never limited by CPU except perhaps when building indexes, so this is a really good optimization. And you can do this just by running these commands. This will be online afterwards, so you can steal these. There's also a separate tweak which applies generally to Mongo, not just on Compute Engine, and that is to separate out your disks, because this will avoid I/O contention. If you're putting your logs, journal, and data files onto a single disk, then you're going to have contention as logs are being written and the journal is being written too. It also allows you to optimize the volume size on any provider, but specifically because that's how Compute Engine works, for the number of IOPS and the size that you need so you can get better value for money. Because the journal doesn't need as much as the database files themselves versus the logs, for example. Now, by default, the logs and the journal are in their own directories, so you can simply mount those as a different mount point on Linux. But you can also do this to your databases as well. And this allows you to really optimize specific databases. You can put a certain database onto magnetic disks, another database onto the SSDs, and maybe another database onto local SSDs, just to move them around and optimize performance versus cost. And you do this by specifying the directory per DB flag when you start Mongo. But there is a warning. If you do this, then it makes using snapshots more difficult. The point of a snapshot is that you take a consistent picture of each of the file systems at exactly the same time. And I've heard of cases where people will just take a snapshot and think they've backed up their database. And if you do this, you're going to find out that your database is not restorable. Maybe in some cases it will work, but generally it won't. And this is because the snapshots are not guaranteed to happen at exactly the same time, and they're not consistent. So you have to either fsync lock the database or shut it down, and then snapshot all the volumes. And it doesn't matter if they're slightly out of sync then, because there's no more writes going to the volumes. So some common problems that you might come across on GC is that the volume size is too small, and Tom mentioned this. You can't just size it based on the amount of data that you need. You have to size it based on the number of IOPS, and the smaller the volume, the lower performance it's going to be. And RAIDing is completely unnecessary except for the local disks, and if you do this, then you're going to have problems. It's all handled behind the scenes. Google guarantees the data that you write is going to be written once it's returned as acknowledgement, so you don't have to RAID for performance or redundancy. And hitting the limits can be a little difficult to find out when that is happening. It could be the VM limit, it could be the persistent volume limit. The monitoring that they provide currently only shows you the disk throughput, not the IOPS. I'm sure that will improve in the future, but it's something you need to be aware of, that it can be difficult to understand when you're hitting those limits. Live migration was also something that they demoed back in March, and this is a really innovative feature. It allows Google to move your VM behind the scenes between hosts. And they'll do this when they're doing maintenance, so they can upgrade the hardware behind the scenes, and you can also migrate around instance failure. It's not something that you have control over. This happens behind the scenes. The only way you'll ever know that this happens is a small note is added into your operations list. And we've had this happen a couple of times in production, wasn't noticed at all. And I worked specifically with the live migration team to test MongoDB, and we tested inserting huge amounts of data into Mongo and triggering a failover, and also deploying Mongo instances across multiple zones and geographical regions, and then triggering a migration, and it didn't notice. Now I'm sure in production we'll probably come up with a case where it does notice, but testing so far shows that this is actually a magic feature. So the next step then, once we plan and we know what we're doing, is to actually replicate onto the other environment. And we use Puppet behind the scenes to manage everything, so it's fairly easy for us to just spin up new instances onto Compute Engine. It's the same with Chef or Ansible or any other config management that you're using. Hopefully you're using something. It makes it a lot easier to duplicate your environment. Databases, those obviously have to be replicated, and this is probably the more difficult part because you're going to be limited on throughput and the security requirements, but Mongo has great replication. This is one of the original reasons that I switched from MySQL over to MongoDB back in 2009, is that replication works really well. And you can set up a replica in the new environment, get it to sync everything over. But if you're going to do this, security is important, and there are two ways that we can do this. First is by using SSL to actually encrypt the transport layer, or we can go a bit lower and encrypt the network and use a VPN. So which one should you use? Well, SSL is a lot simpler because it's built into Mongo itself. It's built into the client, it's built into the drivers, it's built into the server, and it feels less fragile. It's you can just set it up and it just works. Unfortunately, it means that we have to use Mongo 2.6 because although it's available in 2.4, we don't use it currently, and you can't do a rolling upgrade, which means we'd have to shut everything down, switch on SSL, hope that it worked, and then bring it back up again. In Mongo 2.6, you can do rolling upgrades, but we've had problems historically upgrading major versions of Mongo, and so we don't do it. So we want to avoid this, and instead we're going to set up a VPN. The networking on Compute Engine is software-defined networking, and they fully support and document how to set up gateways and VPNs, so you can connect to your existing network, whether it's on-premise or in an existing data center, and have it appear as a network that's accessible within Compute Engine and vice versa. So this is what we're going to do. We're going to connect our soft layer VPN. Well, so we have connected our soft layer VPN, so our private soft layer network appears within Compute Engine, and we can communicate with the instances. And the benchmarks of throughput between the soft layer data center and Google's US region is about 250 megabits per second, which is about the same as the connectivity between two soft layer data centers. So although there's going to be a little overhead because of the VPN and the encryption, it's as if it's another soft layer data center. And getting into a little bit of how we use Puppet, we have four main use cases for it. First is infrastructure, then we use it for standard configuration management, which is what everyone expects, but we also use it for failover and deploys. And we do this because it's a single location, it's the source of all the configuration, it's everything that we do, and it defines in a single place. And when it comes to infrastructure, there are some interesting modules available in the Puppet Forge. One of these is GC_compute. And this allows us to define all of our Google infrastructure within our Puppet manifests. And it means that Puppet will deal with creating them, making sure they're consistent. And we can contain them within the same manifests that define the applications. So the infrastructure and the application are defined in the same place. And we can do this for instances, firewalls, load balancing. Most of the resources that are available on Compute Engine can be defined in this Puppet manifest. And Puppet has support for all the major providers as well. So if you're moving from one to the other, it's easy to define this. It's defined in code, which means we can put it under version control, and we can see who's made what changes and when. And then changes that are made are done so consistently across all of our servers, our entire environment in one go. And because it's in version control, it's in code, then we can apply our code review process, we can apply our coding standards for commenting, and it means it's easy for other people to understand. You don't have to log into a control panel or understand what's being deployed when. It's all described in the manifests that already describe our infrastructure. And this is the same for configuration. It's the standard use case for Puppet and Chef and others, and we use it for a couple of different purposes. For deploying packages, just standard operating system packages that we need. We pin specific versions of packages, so if there's a bug in a known newer release, we can pin to an older one, which is generally how we deploy Mongo, and also defining config files and any tweaks or patches that we have to make as part of normal operation. And we just specify the version that we want to have deployed, so when we're bringing on a new instance, it's not installing the latest version, and so is inconsistent with the rest of the environment. And over the years, we've built up tweaks and changes that are specific to our environment or to work around bugs. And you don't want to be applying these ad hoc to your environment. And so we define them within Puppet. And again, the same reasons apply. It's in version control, and our entire team can see what has been done and when. Code review, all the same reasons. It's not that we're logging into a single server and running commands. We might do that in a test environment, but in production, you don't want to be doing that. You want to do it consistently through Puppet. And we also use Puppet for failover, and we do this by defining our load balancer pools in Nginx through a Puppet manifest, which we've since released. And so we can have all the IP addresses defined within the Puppet database, so that when there's a failover, either we can use the Rake API to automatically make changes, or one of our engineers can go in and make a change in a UI, rather than having to look through documentation and figure out what code, what commands need to be run at 3 a.m., which is when you don't want to be dealing with failover. You want it to be as automated as possible, or if not, as easy as possible to make those changes. And Puppet allows us to do that. Chef has the same principles. It just so happens that we use Puppet. So again, everything is defined within the Puppet database, and it means that it's all accessible through a common interface, through an API or a web interface. And these make up the what we call our documentation. We don't have to write any documentation because nobody really likes writing documentation. It's already documented because actually it defines what our infrastructure is. And so there's no extra effort required. And of course we do have extra documentation to explain some things that can't be explained in a Puppet manifest, and some checklists which are very important. But generally we consider Puppet to be our documentation. So we're coming up to the final stage now, and that's actually switching over to Compute Engine. We've not reached this point yet, but this is how we plan to do it. And we will use the master secondary concept. So we will have SoftLayer as our master, as it is currently. Everything will be replicated into Compute Engine, and it's the secondary. And then at a defined point in time, we will switch, and the roles will be reversed, and Compute Engine will become the primary. And this should just be a case of issuing a step-down command in Mongo, locking the old servers so they don't become master again, and then switching over our DNS. And the only impact that we expect to see on users is perhaps a bit of extra latency, as traffic might go into SoftLayer and have to be routed to Compute Engine. But very quickly, traffic will go over to Compute Engine. Unfortunately, we don't have the luxury of having dips in traffic. Computers are talking to us, not really people, and they're talking to us constantly, and our traffic only increases. It's consistently increasing, which makes this a lot more difficult to do, perhaps scheduling a downtime window. Also, you don't really want to have downtime on your monitoring product, because if you're using us to monitor your stuff, then whatever point in the world you might be and whatever day and time it is, if we're not running, then you're going to have to sit there and watch your servers. So we want to do this with minimal impact. And we use checklists, and this is really important, and it's something that we've stolen from the airline industry, in that we will, in the planning stage, create checklists to go through everything. And so on the day, we will just follow the list, and it will cover exactly what we need to do and when, right down to the command level. You don't want to be winging it and doing ad hoc commands when you're switching over such a large project. If you have fewer servers, then maybe you can do it on a weekend and just do it ad hoc, but really the process needs to be properly documented, rehearsed, and using checklists. Also checklists for reverting. If we have a problem, we need to be able to switch back to SoftLayer where we know everything works. And figuring out that process after the fact is not something you want to be doing. So just some general feedback to how we've found using Compute Engine. Hopefully Google are going to be improving things over the next few months. Google are notoriously secretive when it comes to their locations, and I've badgered the team multiple times to find out where their data centers are. I've written a couple of articles for GigaOM which look at ping to find out where I think they are. This is just interesting for the data centers because I like to know where things are. But when it comes to picking a CDN, it is actually important. And we decided not to use Google storage, the cloud storage product, and use Amazon's CloudFront instead because we didn't know where their edge locations were. And we need to be able to pick a CDN based on where our customers are. So hopefully, perhaps not with the data centers because that's not as important, but maybe with their CDN product, they will reveal this in the future or explain why they can't. At SoftLayer, the luxury that we have is that all the internal networking is entirely free. If you're on AWS, then you pay for this. Within the zone, it's free, but across zones and across regions, then you pay for it. It's the same on Google. You have to pay for your network transit. And this becomes something that you just don't pay attention to and can become very, very expensive when you're replicating databases across zones, as you should do, and especially across regions. And we don't really want to pay for it. So I think Google should make it free. Google also don't support Ubuntu yet. I don't know why this is. I think it's a commercial decision. There's no real technical reason I can see that they don't support it when they support Debian, especially when they support Red Hat and SUSE as well. So I think they need to sort this out and get Ubuntu images up on there. It's not that you can't create your own custom images. You can do that, but it's not straightforward to do. There's an extra effort, and we have to then maintain our images. What we want to be able to do is delete instances when Google release a new image and just start them up again, because often they have bug fixes and tweaks specific to Google. We want to be able to use those. We don't want to have to keep updating our own Ubuntu instances, Ubuntu images. Google also don't have a public status page in the same sense that AWS do. They do have a Google Groups mailing list, which you can subscribe to get notifications when there are problems on their platform, which is fine. But it's better if we have a status page we can go to that we can subscribe to via email, but also subscribe to via RSS. Because one of the features of server density is that we pull in RSS feeds from all the cloud providers' status pages. Because if something starts breaking, you want to know if it's you or if it's your cloud provider. And currently, we have to go to a specific location and see if Google have noticed that this is an issue yet. And though we can find out, it's just a nicer experience if there's a status page with all the services broken down, the current status, like AWS do. And AWS are great at doing post-mortems as well for incidents that they have. Google do this as well. There have been a number of incidents over the last 6 months or so, and they've posted in most cases what has gone wrong and what they're going to fix. It's not quite as detailed as AWS, so I'd like to see some improvements there as well. And there was also a question about code spaces, and the issue there was that someone hacked into someone's AWS console and just did select or delete, which shut down their entire infrastructure, and because they didn't do off-site backups, it shut down their company. Now, the way obviously to mitigate this is to do off-site backups, and Google's snapshot functionality is very good. You can take a snapshot of a file system and store it within the cloud storage, and worth noting is that is then available globally, so you can very quickly restore an instance to a different region, but it is within the Google's cloud storage. So all you need to do is go into the next tab, select all, and delete. So I'd like to see Google implement export for this. You shouldn't therefore rely on this for that particular use case. You need to take your backups in another way. And the way I'd like to see this is that we can export the snapshots into S3 or download them, but probably we would just use S3, and also obviously the import of those. So that's all I have. Thank you very much.